All right, today, at the end of this lesson, so this is lesson 1 of the next unit, which actually is a really good review for lesson 2, or sorry, unit 2. Trying to figure out, do I make this part of the last unit or this unit? Okay. So you'll be able to describe what happens after a net force acts on an object that's moving in the opposite direction of motion for a sustained period of time, and also describe what normal force is and how it acts. Okay. So, demonstration number 1. Let's say we get this thing going. I don't really care about this part, but what I want is what happens when the force acts in the opposite direction of motion for a long period of time and continues to act. Oh, okay. Changes direction. Get to that? Okay, you've probably seen that in the labs, simulations. Okay, it's probably not groundbreaking, but there you go. So, so what happens? It acts in the opposite direction for an extended period of time, slows down, turns around, and speeds back up in the direction of the force. Okay. Which kind of begs a question. Typically, we would make the way it's moving positive, but like if it turns around, like it's going 2 different ways. So really, you just have to pick one and stick with it, commit to it. Okay. But a way that's kind of, you don't have to, but usually you pick the way it's moving initially, make that the positive direction. But give it that. Okay. All right. So let's say I don't care about the pushing part. After it leaves my hand, that's what I care about. Okay, here it is again. Positive, negative direction. Thumbs up when you have a guess. Talk to your neighbor.
Okay. I could have slowed down and then speed up. Oh. Oh, that had nothing to do with it. That's a slow. Yeah, the last I had the opposite.
Correct answer is? Correct answer is B. I've got 2 explanations for you. Number 1, the direction of the net force is always in the same direction as the acceleration. The net force was always acting this way. Okay. Second way is looking at the motion. As it's moving in a negative direction, was it speeding up or slowing down? Slowing down. Therefore, acceleration is in the opposite direction of velocity. So positive. As it was going this way, it was speeding up. Sign of velocity is positive. Therefore, sign of acceleration is also positive. Good with that? Okay. Thumbs up when you have a guess. Have a conversation. All right, what do you say? Correct answer is B. Bouncing bears. Okay. Two explanations. First off, looking at the motion, this chunk here, you're moving in the negative direction, you're in negative land, you're getting closer to zero, so you're slowing down. So if you're slowing down while moving in the negative direction, the direction of acceleration is positive, the opposite of velocity. Here, so here's your turnaround point. Here you're speeding up, moving in the positive direction. So you're speeding up in the positive direction. The sign of acceleration is the same as velocity, which is also positive. What on a velocity versus time graph tells you the value of acceleration? The slope. How do you describe this slope? Positive or negative? Positive. Constant or changing? Constant. A positive constant slope gives you a positive constant acceleration. Talk to your neighbor.
I just did the math. No, it's like and they do like a fishing activity. What? So we do a dead school. At school? Yeah. Here?
Okay, correct answer is A. I just did the math. Said A. Okay. Tell your neighbor. Tell them why you think so.
Okay, what's that I missed? Except for imagine you open because like they're like written questions, you have to grade it. So imagine finishing your test. It says 30 out of 62.
Correct answer is A. What based on one factor? What factoid? Okay. The direction of acceleration will always be in the same direction as the net force. Always. The net force causes acceleration. Okay, they will, like, you can take that to the bank. Okay, good with that. All right. Can an inanimate object exert a force? I have a story for you. So, when I was in college, my roommate in the summertime worked as a whitewater rafting guide / backpacking guide in Colorado. And the tents that they had, their company had, weren't very good. When it rained, it would collect water on the roof. It wouldn't shed the water. It would just like catch it like a bowl. So one of his responsibilities was if it was raining at night, he would have to wake up every hour or so, push up on the roof of the tent, let all the water drain out so it wouldn't collapse the tent. So he did that throughout the summer. Comes back to Purdue. In our dorms, our beds were lofted, meaning they're like bunk beds without the lower bunk. So one night, we go to bed and it starts to rain. And in the middle of the night, he wakes up, hears the rain outside, and sees the roof of the tent above him. He goes to push on the roof of the tent to empty the water out. And as he pushes, it's not going anywhere. It's like, wow, there's a lot of water here. Pushes harder and harder and harder and harder. Gets his other hand up and harder. I wake up to him, both hands, both feet planted on the ceiling, pushing as hard as he can. I'm like, no! Mark, wake up. Like, oh my goodness, I thought I was going to die. Like, this is like. Did the ceiling exert a force on my roommate? So much so that he thought he was going to get crushed. Okay, let me give you a little hint into Newton's third law. You learned it in junior high. It said for every action, there's an equal opposite reaction. Okay. If you put a force on an object, that object exerts a force back on you. Okay. Inanimate objects, we're going to call that a normal force. Okay, the ceiling was exerting a normal force on my roommate. If you're sledding and you hit a tree, does it exert a force on you? Yeah, you should see your face afterwards. It's like something did something. Like, yeah, you exerted a force on the tree, it exerted a force back on you. Okay, we're going to describe a normal force as a supportive force from a surface. Usually it's not as violent as hitting a tree. Okay, supportive force from a surface, and it always acts perpendicular to the surface. Always acts perpendicular to the surface. Good with that? Okay, I want the free body diagram and the setup of me standing at rest. What forces are acting on me? And I've just now opened it up, so like you don't, it's not just horizontal forces. Do vertical forces as well. What forces are acting on me? And do the setup. All right, so we have gravity because we're on the Earth. Okay. Now, there has to be something that cancels out gravity because I'm at rest. And we know that some of the forces are equal to 0. Right? Okay. What is that force? You have a normal force. Where is that from? What object is exerting that normal force? The ground, the floor. If the floor wasn't there, I'm falling. You okay with that? Okay. So, to give you an idea of like where the normal force comes from, imagine someone standing on a trampoline. Does the surface of the trampoline respond to the person standing on it? Like stretches. Okay. It's stretching is what's holding that person up from falling down at normal force. You okay with that? Okay. The molecules of the floor do exactly the same thing, just at a very, very microscopic level. When I stand on here, the floor is like, oh, this guy is going diet, like, does that make sense? There's a supportive force The floor knows, if you could personify the floor, it knows when you're standing on it. Feels it. Just like if someone is walking on your back, you'd feel it. Okay? You're just more squishy than the floor. Get that? Okay, so then we would say some of the forces are equal to 0. We're going to say up is the positive direction. So normal force minus force of gravity is equal to 0. That's the setup. Good with that? So when you do the setup, I would suggest making up the positive direction. That's just a good default mode. Or make up the positive direction. Gravity. Air resistance. Okay. Why? Because it's said to include it. You ignore it otherwise. Okay. Air resistance is going the opposite direction of motion. It's falling at a constant velocity, therefore you know the sum of the forces are equal to 0. We're going to make air, up the positive direction. Oops. So you have air resistance minus gravity is equal to 0. Good there? Next one.
Four of these.
Yeah.
One of those boxes. And you won't use them for anything?
I do.
You do want them? You're going to use them?
I think that's what you use for level. I don't know. Like,
I suppose you could use them for leveling.
I mean, do you want to use them for something else? Or, oh, you're
scavenging. If you don't use it.
Fair enough.
I think they just put all this all the way in. If you screw them all the way in, they're level.
Yeah, but they could be unscrewed. Like as you move the desk.
Right, but if you just crack down with thread, you shouldn't, right?
Yeah.
I mean, what the nuts are for is so you can set them at different heights. Right?
Mm-hmm. Yeah.
Screw back in.
Yeah, but you have to level it and keep it stationary. If you want it level.
If they screw it all the way in,
No.
level. Mine are. None of my tables wobble. I screwed all of them all the way in.
They don't wobble, but they're sorry. They don't wobble, but they're not level.
No. What do you do?
You look at you just go look around like they're. I mean.
So screwing up your rampage, is that what you're saying?
Yeah.
Well, then use your nut.
All right. Thanks. All right. On this, here's the thing. We're doing it of the person, not the elevator. Okay, subtle detail. You got to watch that. So you have force of gravity, and because it's the person and not the elevator, it's normal force rather than tension. If you did the elevator, it would be tension. Because it's the person, it's the floor of the elevator pushing up on them. And so some of the forces are not equal to zero. Normal force minus force of gravity equal to mass times acceleration. Is that? Okay. I want the entire process. Okay. We're going to take, like, when it starts at rest and finally ends at, like, there, like, that whole process. We're going to dissect that up into multiple stages. Okay. So this part here is asking for right there, before it leaves my hand, while it starts at rest, this process here. Process, not just the moment, but like the process of me throwing it, like just freeze frame at one moment in time. Tell your neighbor. Correct answer is B. Good. Okay, we're going to call that applied force rather than normal force because I'm an animate object. Okay. And it's like it's speeding up, so you know that some of the forces aren't equal to zero. Okay, so the net force needs to be up. Good with that? Same stage, same phase is what's the acceleration. Tell your neighbor. Tell them why. Thanks, Lexi. Tell them why. Correct answer is A. Okay. Two reasons. Number one, the net force is up, and you are speeding up while moving in the positive direction. So therefore acceleration has the same sign as velocity, positive. Okay, now this phase or stage is right there. I let go right here. What forces are acting on the ball at that moment in time? Keep it to yourself. Think in your brain. Don't influence or be influenced. Thumbs up when you have a guess. I hypothesize that some people are going to learn some stuff. Talk to your neighbor.
I like your I would probably be lost in this class, which is why you need to switch your study hall. Yeah, about to get the right away.
I like the science machine.
So wait, it's definitely not a force.
What do you say? Correct answer is D. Delicious delicacies of donuts, I guess. All right. So the moment it leaves your hand, you cease to exert a force on it. Unless you're a Jedi. Okay, no. Okay. Once it leaves your hand, you no longer exert a force on it. If there wasn't gravity, it'd just go on forever. He's like constant speed in a straight line path. Because that's what inertia wants to do now, because you put it in motion during the throwing part. Does that make sense? There's no force going up. That is inertia saying, I just want to keep on going. Inertia is not a force. It's just a natural tendency to maintain its present state of motion based on the mass. Good with that? Talk to your neighbor. Tell them why.
You look at me and you're like, couldn't even show up.
I said just that's a compliment. Thank you.
Correct answer is B. Okay. Gravity is the only force acting on it. The net force is down, negative direction, therefore acceleration is also down in the negative direction. As it moves up, what is it doing motion-wise? Slowing down. Slowing down while moving in the positive direction. Therefore, a sign of acceleration is negative. Okay? On the way back down, this is what I want to know as it's falling down before I touch it. Tell your neighbor. That process there, the falling down process.
All the time. I'm surprised.
Sorry. Correct answer is curious. What object is exerting a force upward as it falls down? Oh, so the default mode is always ignore air resistance unless I tell you to include it. So everybody all right with that? Like ignore air resistance. I'm trying to figure out what's going on. That makes sense. Okay, so correct answer is everybody good with D? Okay. Still coming back down. Direction of acceleration. Tell them why for two different reasons. The force reason and the motion reason. Why? Okay, hopefully your conversation sounded like this. Negative because there's only a force. The net force is going in the negative direction. As it falls down, it's moving in the negative direction and speeding up. Therefore, acceleration is the same sign as velocity, negative. Good? Okay. Now, what I want at this is at the highest point. Right there. Right there. What force is? Don't say. I just want you to think what forces are acting on the ball at that moment in time. Just think, don't respond, don't react, don't do anything outside of your head. Just everything's internal without engaging your mouth or your hands or anything. Right, Sophie? I know it's impossible to like not talk. But it's so tempting. Just wait for it. It's coming. Okay, now talk to your neighbors.
Yeah, so once your gravity just goes away. That makes sense.
Yeah, see, there's always I wish I just started answering from Facebook.
I live
I'm
in
like, yeah.
Okay.
You're in it going, jump and now.
What do you say? Correct answer. Dangerous dinosaurs. Okay. At the highest point, it's not like gravity just turns off and is like, sorry, I can't touch that because that's like really high. Yeah, yeah. Okay. Gravity's still a thing. It's still pulling. You okay with that? Don't talk. Just think. Thumbs up when you have a guess. Have a discourse.
You're trying to talk, but you couldn't. You're trying to talk out loud, and you're like.
I just started laughing because all I saw my profile. I was like,
Oh, I'm just carrying chips in my bag. And salsa.
All right, here we go. Correct answer is we're gonna learn some stuff. All right, correct answer for this is what? D, force of gravity. The direction of acceleration will always be in the same direction as the total force. There's only one force acting on it, and that's downward. Therefore, the direction of acceleration is also downward. Okay? Let's talk about it in terms of motion. Okay? As it goes up, what's happening to the speed? It's slowing down. As it comes down, what happens to the speed? Speeding up. But at the highest point, how fast is it going? 0. For how long is it not moving? How long is the velocity 0? A moment. A clock reading. A point on a timeline. How long is a point? It's not. It's just there. Okay? The moment right before the top, was it moving? Yes. The moment right after, was it moving? Yes. Was velocity changing from moment to moment to moment? Yes. Therefore, do you have acceleration at the highest point? Yes. Because velocity is changing the entire time. If it was 0, it'd be like, whoop. Does that make sense? So it's changing. Velocity is changing. Everybody good with that? Okay. Last situation. And this is when I am catching it. This part here. to enunciate this process, pretend like you're trying to catch a water balloon without breaking it. This process happens. That same process happens. It just happens a lot faster when you're just like catching something. But to like think about it, pretend like you're trying to catch a water balloon without popping it. So it's not at rest in your hand. It is this part, like the catching. It ends up at rest, but the process, that process. That process. Dr. Neighbor.
Is it like kind of from like the high point? So when you catch it, like the whole
This part here.
of that.
Just this part. Just that part.
But I still heard it's not at rest.
What?
So the arrows won't be the same length. Yeah, but you're saying. I guess I definitely.
Okay. This picture, these two arrows are identical in magnitude. Actually, let's do this. I have a theory. Let's do this question first. Tell your neighbor. Tell him why. What's happening to the ball? Slowing down. Which way is it moving while you're catching it in the process of catching? Negative. So if you're slowing down while moving in the negative direction, the sign of acceleration is positive. And therefore, correct answer is B, because the net force has to be in the same direction as acceleration. Okay? You're exerting more force to slow it down because its inertia wants to keep on going. You're like, no! You're putting on the brakes. If you ever caught anything like a brick or something really heavy, you're like, ugh! You got to exert more force than it weight, like a lot of force. And then, all right. Good? Okay. Got a review worksheet due on Monday. It's on Canvas. I'm baking a mastering assignment currently. I'll post that. That'll be due on Tuesday. Yep. Test on Tuesday. So the registration code for mastering is in the intro module on Canvas. Are you in Canvas like doing it?
I'm not.
I'll email you all.
What were your words? I thought it was so good.